Okay, so couple of notes. I graded the Unit 1 exam. So I went through any problem that was marked wrong by WebAssign, I manually reviewed. And, a lot of times there were things like missing a plus C, or maybe say in a long integration problem, say one constant or a sign or something like that was off. Or maybe there was a pretty clear, mistake, like say 1 over x4 instead of x to the power 4, or something, like just a syntax error like that. And I gave, full credit for things that were obviously just kind of typo type things, and partial credit for things that, like missing a plus C, for most of the problems would just knock 2 points off. But obviously WebAssign is going to take off all, let's say 12 points. So I would give you, say, 10 of those back. So I made the adjustments. Unfortunately, a WebAssign, I can't make the adjustment problem by problem. I can't go in and say, hey, problem 4, WebAssign, you said it was 0 out of 10 points. I want problem 4 to be 7 out of 10 points for this student. The only way I can make an adjustment is to give an overall adjustment to the exam. So I enter it as a bonus, and that makes the adjustment manually that way. And then I do note, I think the notes only come through on my side though, but I do note each problem and how many points I awarded for it, and kind of roughly like what type of mistake it was, or what type of partial credit I'm giving you for it. So if you have questions about the details on, what points you were given for which problems, shoot me an email and I can really easily just go and send you over my notations and a little bit more detail on why something was graded a particular way. But yeah, definitely check your updated exam grade. The updated grades are in there. The plan today is to start differential equations. DiffEq is it's a component of Calc 2. It's also kind of in its own right. It's a whole course that we offer. So in a sense, we're scratching the surface of differential equations, and how far we go into differential equations just kind of depends on how time progresses and so on. So the goal will be to touch on these 4 topics. Well, I suppose, maybe even before direction fields, basic, what is a differential equation? And then direction fields, essentially a graphical solution method for differential equations, separable equations, a fairly one of the simpler approaches to solving a differential equation algebraically, getting an algebraic solution. First order linear, another fairly straightforward approach. And then some basics of second order differential equations. So that's the plan for the next couple of class periods, as well as the next, well, not the next supplement, but next week's supplement. The supplement for this week will be focused on chapter 8, some of the applications, but next week's supplement will be focused on differential equations, and perhaps even the week after that supplement, just depending on how things go. And as I mentioned on here, the supplement on some of that chapter 8 material will be posted later this week. The quote of the day today is more of a meme of the day. I actually just saw this pop up on Facebook yesterday. There's a media outlet that makes comics called XKCD, and they make a lot of these kind of like funny comics with these stick figures. They're usually about nerdy things, about computer programming or math or science or something. But here one guy is saying to the other, when a metric becomes a target, it ceases to be a good metric. So maybe in a business, they want to provide something valuable to the economy, to society, and they say, do we think we're doing a good job of that? Maybe we establish a metric, a number that informs us whether we think we're doing a good job of that. But then it tends to be the case, because a number is pretty objective, that we, instead of focusing on saying, how can we better serve the public? How can we better provide value to the economy? We shift our attention to the number and say, how can I better make this number go up? And that might sound like it's answering the same question, but or asking the same question, but in a lot of cases it's not. And then of course, the joke is the other guy says, oh, that sounds bad. let's offer a bonus to anyone that identifies a metric that has become a target. And, probably a week from now, they'll have their employees have found, 500 metrics that have become targets because that's what they've incentivized, right? They haven't incentivized retargeting. They've incentivized finding metrics that have become targets. So be careful with what incentive structures you create if you're, say a supervisor or manager over folks, and be cognizant of what incentive structures your managers or your supervisors are creating for you, and ask yourself if those incentive structures are really in line with what the business or the entity maybe ought to be doing, with what its mission ought to be. Okay, so moving into differential equations. What is a differential equation? It's an equation relating a function to one or more of its derivatives. The most basic non-trivial example of a differential equation is something like this. Say y prime equals y. Here I have a function y of x, and I want to find the function y of x such that when I substitute it in over here, this becomes a true statement, right? If I have, 3x plus 1 equals 4, I have a number x. I want to figure out which number I can substitute in for x such that the left side and the right side are the same thing, that those expressions are equivalent. Note the difference. Here I'm searching for a function, where in algebraic equations, I'm searching for a number. So does anybody want to hazard a guess at a function y, that is its own derivative? Well, I think maybe e to the x would do, right? Y prime is e to the x, which is y, and I note that I've got y prime equals y. This represents the solution. I know that I can have, say, in algebra, I can have maybe a linear equation like the one I wrote up there that has a unique solution, that has one number that's a solution, or I could have an equation like x squared equals 4 that maybe has more than one solution. Is there another solution to this? Well, if I thought of maybe 2 times e to the x, y prime is also 2e to the x, and that is just y. Or really, an arbitrary constant times e to the x. Its derivative is going to be the same thing. That is a solution. If I kind of think a little abstractly, if I say had a quadratic equation, x squared equals 4, to kind of undo the quadratic bit and get the x out of there, I square root, right? If I had like a 1 over x equals some number, I would invert. If I have a derivative and I want to kind of undo the derivative, in some sense, I'm integrating. In some abstract sense, I'm integrating to get rid of the derivative. I know that integration pops out an arbitrary constant, right? Integral of x dx 1/2 x squared plus c. In other words, there is a family of functions parameterized by this constant c that represent this integral, that represent this antiderivative. So 1/2 x squared plus 0, 1/2 x squared plus 1, 1/2 x squared minus 100 are all solutions in some sense to this problem. I have the same thing here. I have what it amounts to a constant of integration coming out of the general idea of kind of undoing this derivative. That gives me a family of functions that are solutions to this differential equation. So what do my solutions look like? Maybe if a was 1, I get a solution looks like that, y equals e to the x. If a was 2, if a was, say, -1 or -2, of course, a doesn't only have to be integers, but I'm just showing some integers. And I'm going to draw this one in green just so we can see it. There is a solution right here along the x-axis corresponding to a equals 0. The 0 function, where for whatever input the output is 0, is also a solution, right? It's y prime, its slope is 0, which is also what the value of the function is everywhere. Okay, so we have differential equations that look kind of like this. This equation we would call a first order ODE. First order ordinary differential equation, as opposed to a partial differential equation, which is a little more complicated version of a differential equation. We call it first order because the highest derivative we see is one derivative. So it's first order. First order differential equations is what chapter 9 focuses on. We could also have higher order differential equations, second, third, fourth, whatever. But it tends to be the case that first order differential equations are quite important for a lot of applications. And second order equations are also tend to be pretty important. Maybe the higher order equations are a little less important. Also, the solution methods, the strategies for attacking solving these differential equations are a bit different between first and second order, but from like second up to third or fourth or fifth, the kind of general strategy is fairly similar in a lot of cases, maybe I should say. So maybe an example of a second order ODE would be something like y double prime plus y equals 0. These differential equations, the equations themselves work like any other algebraic equation. We can move stuff from one side to the other. We could subtract y from both sides, and we could say, in other words, what I'm asking for is a function whose second derivative is negative itself. So y double prime equals negative y. Can I think of a function whose second derivative is negative of itself? Maybe sine x. Its derivative is cos x. The second derivative is negative sine x, which is negative y. If I had 3 sine x or negative 5 sine x, that would also be a solution. So I could say a times sine of x. We might also happen to realize that another solution might be something like cosine of x. cosine's derivative is negative sine's derivative is negative cosine, y double prime equals negative y again. And of course, I could multiply by a constant, and that constant is just going to carry through. That doesn't affect this being a solution. I might even realize that if I take the sum of these two functions, I have two functions, each of which is independently a solution. These aren't like terms. They're not like basically just the same function written a second time. These are fundamentally different functions. If I add them together, well, derivatives split sums apart and everything should work pretty nicely, right? If I consider y of x equals a sine of x plus b cosine of x, you could go through the details, but this will be a solution as well, either just by the linearity of differentiation or by going through and computing y prime, y double prime, and noting that y double prime is indeed negative y. So this is a more general solution, right? I can actually see that the top left solution, a sine x, is just this bottom solution with my constant b set equal to 0. My top right solution, b cos x, is just this more general bottom solution with a set equal to 0. So those are just special cases of my more general solution. This solution encapsulates all of the other smaller, in a sense, solutions that I found already. Something interesting I see here, this is a second order differential equation because it has two derivatives. It has let me be careful how I say this, it has a second derivative on one of the functions. So one of my terms has a second derivative. To, in a sense, undo two derivatives, I would have to like perform two integrations. If I perform two integrations, if I integrated this dx, I would get some other stuff plus another arbitrary constant, right? This would turn into a cx, this would turn into whatever it is, but we would have two arbitrary constants if I did kind of a double like nested integral kind of. We haven't talked about that, but I think we can understand that just like derivatives, if I think of taking a function, applying the derivative to it and getting another function out, I could then differentiate that function and get another function out. I could do the same thing for integrals, no problem. We maybe don't use that quite as often, but there's nothing keeping from doing that. And I would see that I would get two constants out. And again, that meshes with what I see down here to, in a sense, undo two derivatives. I end up, in a sense, in a loose sense, doing two integrals and getting two constants out. Okay, so just to recap, important bits. We have first and second order differential equations. The solution to a differential equation is a function, and the most general solution to a differential equation is going to be a family of functions parameterized by one constant, one arbitrary constant for a first order equation, and two arbitrary constants for a second order equation. So far, we looked at some simple equations, and our strategy was basically guess and check. That's not a bad strategy, right? If the equation is fairly simple, there's nothing wrong about just saying, can I guess the answer? As long as you rigorously and carefully check that that answer is correct, that's not a bad strategy. So I guess we've already actually uncovered our first differential equation solving strategy, guess and check. Right? I mean, that's a little bit of our basic strategy for, say, integration techniques. If we think of our hierarchy of integration techniques, the first thing that we would ask is this an easy integral to do? If it's just integral of x squared, I'm not going to look for a substitution or something crazy. I'm just going to essentially guess and check. I'm going to say, do I just happen to recognize x squared as the derivative of some function, and I can apply fundamental theorem of calculus. That's kind of what I do here. Do I recognize this relationship as being a relationship between a function and its derivative or its second derivative for a function that I'm familiar with? And if I do, maybe I can use that either just to get the full solution, or at least as maybe a jumping off point, or something to give me an idea of what the solution might look like or a direction I might want to take. Okay, so what if we have a differential equation that's not trivial to solve? What if I have a differential equation where I can't just come up with an educated guess and get the solution? Well, I would like to develop some techniques, some algorithmic methods that I can use to generate a solution, either algebraically or numerically. So just something to recall is that we have three ways to describe a function. I suppose perhaps somebody might say there are four ways. You might say we could describe the function in words, but three ways that we typically use. The first is algebraically. So something like y equals e to the x. The second is a table of values. So we could have a set of chosen inputs. And associated outputs, a sampling of points on the graph. And the third, a graph. Now, most of the time, the goal is to get an algebraic representation. From an algebraic representation, I can derive the table of values and I can derive the graph. Right, so going left to right, I can do. So if I have the algebraic representation, that kind of gives me the other two in a loose sense. I can generate the other two from that. If you just give me a table of values, I can't infer what the algebraic structure is. If you just show me a graph, I can't definitively say what function it represents. I might be able to make a pretty good guess based on the graph or the table of values, what the algebraic relationship might be, but I can't say it definitively. So quite often we are interested in getting an algebraic solution, and that's going to be the case for basically all of those three: separable equation, approaching solving first order equations that are separable, that are first order linear, and our second order techniques that we'll talk about. Those will be geared toward getting an algebraic representation of the solution, from which we could get tables or values or graphs or anything that we need. But sometimes maybe getting an algebraic representation of the solution is impossible. Sometimes it might be infeasible. Sometimes it just might be a lot of work and we just want an answer quickly. Right, maybe I have a differential equation model and I want to tweak this and tweak that, and I don't want to have to resolve the thing every time. Maybe I just want to directly get a table of values or directly get a graph to let me know what that solution is, let me know what some of the behaviors of that solution are going to be. So there are a lot of different ways to get tables of values directly from a differential equation without going through the algebraic solution. This is actually really like a whole field, a whole mathematical field. You could do a whole PhD in this. You could spend a career researching just ways to do this. This would be called something like numerical analysis. So numerical solutions of differential equations. And we'll look at one. I'll probably do this in the supplement. We'll look at one called Euler's method, but there are other methods. There are the set of Runge-Kutta methods are particularly widely used. There's Hoyne's method that kind of builds directly on Euler's method. There are a ton of methods in this this field, numerical analysis. We can also actually directly get a graphical representation for a first order equation without going through the algebraic structure. And the way that we do this is we use a tool called a direction field or a slope field. So if I want to get a graph, a picture of the solution, or of a solution, or maybe even a picture of several members of the family of solutions, I can start by constructing a tool called a direction field or a slope field. I can then use that to just directly construct some graphs of members of the family of solutions. So this is what we're going to look at next. We're going to try to get a graph of the solution without solving the problem algebraically. Okay, so moving on. Oh. Okay. So let's suppose we have a first order ordinary differential equation, or just differential equation. Let me zoom in just a little bit here. If you're on a small screen, make it a little easier to read. Okay. We're going to suppose that we have the differential equation written as dy dx equals f of xy, or y prime equals f of xy. Now this has an algebraic interpretation that the derivative of the function I'm looking for is equal to some other relationship between x and y. But this also has a direct graphical meaning. What it means is that for each point in the xy plane, I can evaluate f at that point. So maybe here x is 1 and y is 2. I can evaluate f of 1 comma 2, and y prime at that point, when my solution, or if a solution passes through that point, its slope must be this number. Maybe this number is, let's say, 1, for instance. For some function, for some particular differential equation, maybe we evaluate that right-hand side at x equals 1, y equals 2, and it gives an output of 1. This tells me at 0.12, 0.1 comma 2, x equals 1, y equals 2 on this 2D plane, if a solution passes through that point, its slope has to be 1. Or in other words, the slope of its tangent line has to be 1. I could draw a little, let me zoom this in a little bit more. I could draw a little chunk of a tangent line through this point 1 comma 2 with slope 1. I could do this for a whole bunch of different points. I could do this for 1 comma 1, or for 0,1 or 0,2 or 2,1, 2,2. Or I could do this for a large sampling of points in this 2D coordinate system. And then we'll see that I can actually use that information to kind of basically guide my graph. I could start on the left, kind of work my way to the right, and just kind of follow those tangent lines to guide the picture that I can draw to approximate the graph of my function. I can kind of think of them as, in a sense, like if water is flowing left to right and I drop a ping pong ball at one point, where is that ping pong ball? Like, what path is it going to follow? Where are the currents going to take it? Okay, so let's try to do this for an actual problem. So here we're going to look at a population dynamics problem. And as an aside, for it, in a DiffEq class, we would probably spend, we spend pretty much a whole day talking about what is this, what are different applications, and so on. We would spend probably the better part of a month or so going through all of the first order techniques and details and nuances. So, that there's still a lot to be gained from taking the DiffEq course. But again, we're just kind of scratching the surface, and this is moving at a little bit of a faster pace, or really a lot of a faster pace than a DiffEq course would move, but also the expectations are lower, right? The types of problems that you'll be asked to solve are going to be simpler than those in the DiffEq course. So this is moving at a fast pace, but it's also a pace where we're just covering things topically rather than really in any great depth. Okay, so let's consider this population dynamics model that's called the logistic model. And here we have a function p of t representing population at time t. dp dt, the rate of change of the population with time p, or rate of change of the population with respect to t. Let's forget about this 1 minus p bit here for a minute. Let me just delete that for a second. And let's just think about this equation. Or in other words, p prime equals 2p. What this is saying is that the rate of change of my population, something like the number of new individuals added to my population per time period, is twice what my population is. If my population is 0 at a certain time, then p prime is 0 at that time. We don't add any new population members. So we have an equilibrium solution, p equals 0. So p equals 0 is actually an equilibrium solution. My population could start at 0. It would stay at 0 forever. It would never move away from that. If I have some folks in my population that yield some growth rate, if I have twice as many folks in my population to start with, the growth rate is twice as high. If I have twice as many people in my population, there's going to be twice as many births as if I just had 1 times that amount of people, right? That seems pretty simple. This is called the Malthusian growth model. And we can see that this looks very much like the y prime equals y example up here. It's going to be an exponential as a solution. So we'd get something like p of t equals maybe something like e to the t, but I see that I want the derivative to be twice the original function. I need a power of 2 up there as well. E to the 2t, when I differentiate that, the chain rule pops out a factor of 2, and I get p prime as 2 e to the 2t, which is 2 times p. Okay. If I look at this, though, one of the shortcomings of a model like this, the Malthusian model, is this exponential growth. I mean, at some point, we're going to have more people than can like physically stand on the earth or something. Are we going to dig underground or what? I mean, way before we get to that point, we're going to get to the point where we can't support the people with the amount of food we have or whatever. So that's where something like this logistic model comes into play. Let me just undo all of this, and that's what we're going to investigate. We're going to investigate the logistic model that builds off of this Malthusian model. We have this extra factor here. What does that do? So here I'd like to answer a couple of questions first. Well, I know that dp dt this represents slopes of the tangent lines at certain points, right? I have my solution, p is a function of t. At different points, I'll have different slopes. Where are the slopes positive, where are they negative? Let's start with where are they zero. Well, for p prime to be zero, that means 2 times p times 1 minus p has to be zero, or that means p equals zero, or p equals 1. Remember, in that basic Malthusian model, we had p equals 0 was an equilibrium solution. We had, if our population was 0, the slope was 0, we don't add or subtract anybody from the population, so a little bit later, the population is still 0. The slope's still 0. There are no births or deaths or whatever. I don't know if you can have deaths and negative to go to negative people, but population is still 0. The population level doesn't change. A little bit later, the population is still 0, and so on. That's an equilibrium solution. We actually pick up a second equilibrium solution, p equals 1. If I consider p of t equals 1, the function where for whatever time, whatever input, we just give the output 1, that has slope 0. So dp dt would be 0. And plugging in p equals 1 yields a 0 on the right side as well. That would be a solution. It's an equilibrium solution because over time, over changes in the input, the output doesn't change. In other words, this represents something like a carrying capacity. Once our population reaches 100% of its of the possible level that can be supported or whatever, our population doesn't get any bigger, and it also doesn't get any smaller. Populations tend to want to increase. I mean, if we just look historically, it tends to be the case that the number of people on Earth has increased over time. But this provides the upper bound. So this is maybe a positive development over the Malthusian model, because we now have an upper bound for population built into our model. We're not saying our population just goes to infinity. Okay, so when are the slopes 0? When p is 0, when my position is 0 on the vertical axis, regardless of time, regardless of what the t value is, or when p equals 1, regardless of t. That's when the slopes are 0. When is p prime bigger than 0? And when is p prime less than 0? For this, I'm going to come over here and draw a picture. This is not the solution p of t. This is just a picture that I'm going to use to help me answer this question. I see that p prime depends only on t. It does not explicitly, did I say that p prime depends only on p, does not explicitly depend on t. It only depends on p. This type of equation gets a name. It's called an autonomous equation. Auto meaning self. So it's kind of like self-named. It's p prime only cares about p itself, It doesn't care about t, the time, the independent variable, the input. Since p prime is only a function of p, I can actually just write p prime as a function of p. I can treat these as two different variables, p being the quote input in this sense and p prime being the quote output. And I can figure out for what values of p is p prime positive, negative, or zero. We know when it's zero is when p is zero, or when p is one. We've already found the zeros on this graph. When p is between 0 and 1, strictly between, 2p is positive. 1 minus p, 1 minus a number that's between 0 and 1 is also positive. And we know that 2p times 1 minus p is a quadratic opening downward. So p prime is positive for p is between 0 and 1, negative otherwise. And so I now know where my slopes are positive, where they're negative, and where they're zero, representing equilibria. I can actually come over here on this picture and even add one more piece in. If p is between 0 and 1, what happens? If p is between 0 and 1, remember, there's no explicit dependence on t. Super important for this analysis. If p is between 0 and 1, p prime is positive, p is increasing. So if I were to start here, I would be headed to the right over time. If p is bigger than 1, p prime is negative, p is decreasing. If p is less than 0, p prime is negative, p is decreasing. This picture is going to be super helpful in answering the next question. What are our equilibrium solutions? What are the solutions, p of t, where it's just a constant and then stays at that constant forever? My equilibria are at 0 and 1. We might think of an equilibrium solution as having a characteristic of stability. In other words, if I have a population that's kind of near the equilibrium solution, p equals 0, but not right on it, does it tend to kind of stay near there, or does it tend to go away? Or what about with p equals 1? If I have a population that's near population value 1, but not exactly 1, does it tend to stay near 1 or get closer to 1, or does it tend to go away? As kind of an analogy, imagine that we have, say, a valley and a hill, and here's somebody playing soccer, kicking a ball on the valley and through the valley and through the hill. And imagine I have a soccer ball at the peak of the hill and a different soccer ball at the bottom of the valley. Now, this soccer ball that's perfectly sitting at the very tip of the hill, it's at an equilibrium position. It doesn't want to go right or left. It's right smack in the middle. And same with the one at the valley. It doesn't want to go left, doesn't want to go right. These are both equilibria, but one is stable and one is not. In other words, if I take this ball at the bottom here and I give it just a little tap, right, just a little kick, not so hard a kick that it goes over the next hill, but just a little perturbation, what happens to the ball? It just kind of settles back down to its equilibrium point. This is stable. In the valley, if the ball is near the equilibrium point at the bottom, it's going to stay near the bottom. If I take this ball at the top of the hill, right at that crest where it's perfectly balanced, and I give it just the tiniest little nudge, it moves over a little bit, but now it slopes down. But now it wants to move to the right even more. It encounters a steeper slope, making it want to move to the right even more. This is an unstable equilibrium. If I'm close to, but not right at that peak, my ball is going to either fall to the right or it's going to fall to the left. The only way that I can stay balanced at that peak is if I'm perfectly right on that equilibrium. Again, where the valley, if I'm close, it's going to stay close. Right? When it goes to the right a little bit, the slope that it encounters pushes it back in the direction that it came from. Whereas up here, when it moves a little bit, the slope it encounters pushes it further away from the direction it came. In fields like engineering, this is sometimes called negative feedback. In other words, the feedback from the system being like the valley and the hill, the feedback provided to the thing that's interacting with that system, the ball, is that in the valley, if it goes to the right, the system pushes it back the way that it came. It opposes deviations from where it was before. Where up here, we have positive feedback. So you might hear like a positive feedback loop, or if you've ever, somebody is holding a microphone and they walk in front of the speaker and you get this positive feedback where the microphone amplifies the sound that it hears, and there's some little speck of sound somewhere, goes into the microphone, comes out of the speaker at 10 times as loud, but that goes back into the microphone. And then the microphone amplifies that 10 times as loud sound back to the speaker at 10 further times as loud. And you get this, runaway phenomenon. This is positive feedback in the sense that when I deviate to the right, the system wants to push me more to the right. Instead of providing balance, it provides this kind of runaway phenomenon. Okay, so where are the equilibria? We found that. Which one is stable? Which one is unstable? So looking at this, let's pick blue. If I'm at 0, if I go a tiny bit to the left or a tiny bit to the right, I can see my green arrows. I can see my P gets pulled away from 0. P equals 0 is unstable. In other words, if I have a population that goes from 0 to somehow spontaneously a few folks, then those few folks will have a couple of kids and they'll make more folks, and those more folks will have more kids, and then we start growing away from 0. Whereas P equals 1 is stable. If I have a certain amount of people that can be fed based on a certain amount of land or resources or whatever, if I go above that, especially in, for things for, say animals, for instance, I mean, people tend to, if we start to go above that, we find creative ways to use our resources better, usually anyway. But animals, for instance, who are just dependent on the land and a little less able to do that, if you get a bit of overpopulation, then there just aren't enough resources to go around. Some of the population dies off, brings you back to that maintenance level. If you are below what the system can support, then you can still keep growing your population, like under the Malthusian assumption, where births outweigh deaths. This is stable. If we're at carrying capacity and a sickness or something comes through and kills off some of the population, it'll grow back up to carrying capacity. If we, for some reason, end up over carrying capacity, maybe a whole new herd of deer or something moves in. Are they called herds? I don't know. a whole bunch of deer moves into an area for some reason or whatever, and now there's too many deer in the area for the system to support it. Some of them will die off and bring it back down to that carrying capacity. Okay, can solution curves cross each other? And I think typically the answer to this is no. And the answer is uniqueness. There is some nuance to this. Again, this is not intended to be a full DiffyQ course. We have theorems that are called the existence and uniqueness theorems that lay this all out very clearly and precisely. But basically, let's suppose that I had one solution that went like this, and I had another solution curve that went like this. Well, if I start at this point, and then I go to the right, if I say progress over time, which one should I follow? Which path does my system follow if I start at the point of intersection and then progress, say, out to the right? Now, I mean, me saying that it wouldn't make sense for this doesn't mean that it can't happen mathematically. But, again, I'm giving a hand wavy argument here. This is not intended to be a full treatment of DiffyQ. But essentially, the point is we want uniqueness of solutions for most, nice, pretty reasonable differential equations. Solution curves will not cross one another. You can come up with crazy ones where maybe that's not an assumption that can be made, but for most reasonable ones, solution curves will not cross each other because we have uniqueness. Okay, so now let's try to draw a slope field by hand. I'm going to, again, be leaning heavily for this problem on the fact that there's no explicit dependence on t. I'm going to focus on t bigger than 0, and I'm also going to focus mostly on p bigger than 0. So one thing that I would like to start with is my equilibrium solutions. I know anytime that p is 0 or 1, I have a horizontal tangent. I'm going to come in here and consider some sample points. So I might make myself a grid, t going from 0 to 3, and p going from -0.5 to 1.5, in increments of 0.5. Now remember, when p equals 0, p prime equals 0, that's a horizontal tangent. I'm going to come down here at, say, for instance, t equals 0, p equals 0. I'm just going to draw a little horizontal line segment. When p equals 0, I have a horizontal tangent. I'm just going to draw little line segments representing the tangent lines at those points. That's going to be the same regardless of what t is. Here we're really leveraging that lack of explicit dependence on t. Similarly, whenever p is 1, regardless of what t is, I have a horizontal tangent. So at each of these sampling points, any solution curve that goes through, say, 1, 1 has to have a horizontal tangent there. Any solution curve that goes through 2, 0 has to have a horizontal tangent there. At p equals 1/2, again, regardless of what t is, at p equals 1/2, I have a positive slope. I'm not going to worry too much about how positive it is. I'll just draw it as a positive slope. And again, the slopes don't explicitly depend on t. So when p is a half and t is 0, I have some positive slope. I have the same positive slope when p is a half, t is 1, or when p is a half, t is 3. And then likewise, when p is below 0 or above 1, I have a negative slope like this. And now I can imagine that, say, a stream of water is flowing left to right with some of these eddy currents between 0 and 1, kind of pushing it up, pushing the water up, above 1.5, pulling it down. I can imagine putting, say, a tennis ball here at, or not a tennis ball, a ping pong ball here at like 0, 1. It's going to get pulled straight across. It's going to follow this equilibrium solution. This is one solution to our equation. Same with a solution starting at 0, 0. It's going to stay at 0. This would be another solution. This would be a P of t that's a solution. This is a direct graphical technique for drawing solutions. Another solution here, p equals 0. We have solutions in between 0 and 1, in between p equals 0 and p equals 1. Remember our constraints, they have to follow these tangent lines. So as they get close to 1, they've got to start getting close to a horizontal tangent. Same with as they get close to 0. In between, they have to have a positive tangent. And they can't cross either of these equilibrium solutions. These like intermediate solutions have to look something like this, and they really can't cross each other either. So these are some other solutions, some other members of the family of curves that represent solutions to the differential equation. And we have some others that look like this, negative slope approaching a horizontal tangent. It shouldn't, I didn't mean to run into that one, but we see that when we're overpopulated, the population decreases to the carrying capacity. And down here, we have solution curves that look like this. These aren't really sensible solution curves in the sense of a population model. What does it mean to have negative population? But maybe if we were using this to model something else, maybe in that case, a negative output could make sense. You know, maybe it's we're modeling voltage or something instead, and then negative voltage just means kind of going the opposite direction. So that all of these green curves, this is a representation of some of the members of the family of curves that are solutions to this differential equation up here. And we got it by a direct graphical approach. We didn't find P of t equals something and then graph that thing. We just got the graph directly. So when we come back, we'll talk about using this applet or another online tool to replicate this, and then use that to look at some of these problems down here. And then we will move on to separable equations. So that'll be the plan for next time, to wrap up this and separable equations, and then first order linear and second order coming after that.